So, hello guys. So, welcome to the fourth part of my lecture series on cosmology. So, in the previous lecture, we've seen about the curvature types of particles in the universe, and then about Robertson-Walker metric and the the concept of proper distance. So, all of these, have to have we have come across with the ways that we can express, the way in which the universe expand and how our observation based on it also has to vary with our data due to the expansion of the universe. So the expansion concept of expansion was discovered recently only. So we discarded the uh, Newtonian concept, like curvature of the universe. So we discarded the Newtonian concept understanding, and we just switched over to Einstein's general relativity understanding to explain stuff about the universe according to the curvature of the universe due to the presence of mass and energy on the space-time continuum. So in this part, we'll first deal with what's called as the Friedman equation. So in the previous segment, we have seen about the curvature as if the curvature factor, that's k, that is if k is equal to 1, it is a positively curved surface, and if k is equal to -1, it's a negatively curved surface, and if k is equal to 0, it's simply a Euclidean or a flat space. So we have seen we have seen a way to express this mathematically also. So say we a thought experiment, like we draw or we construct a big triangle on the uh, surface of the space. So according to that, the sum of the angles of the triangle at the vertices will also change. It will increase or decrease with the change in the curvature in the space. So for a positively curved surface, the angle will be greater than pi radians. The sum of the angles will be greater than pi radians. For a negatively curved space, the sum of the angles will be less than pi radians, and for a flat space, it will be exactly equal to pi radians. That is what we have seen in our in the previous lectures. So we also know so now let's move on to the Friedman equation. That is one of the most essential equation in cosmology. So uh, in the 19 like actually the curvature of the universe was not exactly thought about first by Einstein. So it was actually thought about first by a scientist called as Nikolai Ivanovich Lobachevsky. So he was able to, through his observations, he was able to come to an understanding about the curvature of the space and how the space is positively curved. And after that, Einstein, had taken over the idea by using his theory of general relativity to back it up. So, scientists had a general understanding about the universe, curvature of the universe, right? Even before Einstein. So, first, to come to an understanding of Friedman equations. So, we'll first look at the main essential part, that is, the Newtonian aspects, as all we've derived is derived from, or the laws we initially had about the universe had come from Newton's laws of gravitation. So we can express the Poisson's equation. So like how the Einstein's field equation, is the key equation, is the key part in plays a very crucial role in general relativity. So the same way, the Poisson's equation plays a very crucial role in Newtonian dynamics. So the Poisson's equation is given by Laplace square of phi is equals to 4 pi g times rho. So excuse me. So the phi is here is the gravitational potential, and then you have 4, and then g is the universal gravitation constant, and rho is the mass density at that point. So we can also, by taking the gradient of the potential of the gravitational potential, we can determine the acceleration, and using that we can determine the trajectory of objects moving freely through space. So this is about the way using Newtonian dynamics. But on the other hand, Einstein's field equation gives a mathematical relation between the metric of space-time at a point and the energy and pressure at that specific space-time point. So this is the the sort of difference between the concepts, between the two concepts. And in cosmology, so we've seen using Einstein field equation and Robertson-Walker metric that we've seen in the previous lecture, we can find the equation that links the scale factor, time dependent scale factor, the curvature factor, and then the radius of curvature of the universe, like of the curved surface of the universe. Yeah. So, and then we also have the energy density and the pressure, which gives us an idea about the contents of the universe. So the equation that relates the time-dependent scale factor, the curvature factor, the radius of curvature of the curved universe, and the energy density is known as the Friedman equation, named after Alexander Alexandrovich Friedman. So to give a background about Alexander Friedman, so he started off as a meteorologist, and then he taught himself the theory of general relativity and many other and basic idea of the basic understanding of cosmology that people had at that time, and then he tried to come up with his own way to express the laws of the universe. So he actually had had an a good understanding as to how the universe expands or contracts as a function of time. He had already proposed the idea at that point using his own theory and calculations. But since he wasn't a well-known scientist at that point, so people hadn't given much notice to his work. And even after it reached Einstein, he was like, it's not legible enough, and it's just a mathematical concept, and it is not applicable in the universe that we live in. But after the Hubble's law was established and was known to the world, and many then they tried to relate his work with the Hubble's law, and then they found out that this actually makes sense, and Friedman was actually right. But by the time his equation and his law was brought out to the world, by the time he had already passed away. It was only because of hepatitis, because of typhoid. So he had passed away, and he was not able to know that his work was actually recognized by the world, and it was celebrated as much as it is in the present day. So this is about his background. So let's go to what he did actually. So he derived this equation from Einstein's field equations using the full power and the full capability of theory of general relativity. So first let's assume a homogeneous sphere of matter with total mass ms, and that's constant with time. So the sphere is expanding or contracting isotropically, so that its radius rs is increasing or decreasing with time. So this is basically the expansion of the universe. So expansion or contraction of the universe. Sorry. So place a test mass of infinitesimal mass m at the surface of the sphere. So from what we know, like from Newton's laws of gravitation, we know that the force due to gravitation is given by g mm by r square. So in this case, g ms, that is the the mass of the sphere, and then m is the test mass kept on the sphere, and rs is the radius of the sphere, which is only dependent on time and doesn't depend on anything else. So this is from Newton's laws of gravitation. First, in this case, we'll try to understand his equation and derive it based on Newton's understanding of Newton's laws. Okay. So from that, we also know that the gravitational acceleration at the surface of the sphere is given by minus gms by rs, which time dependent rs square. So this is the acceleration due to gravity, and then what we do is multiply each side of the equation by drs by dt, and then we integrate the equation with respect to time. So we get equation number 4, that is 1 by 2 dErs by dt whole square, that is equals to gms by rs of t plus u. So if you look closely upon this equation, so you'll understand this is basically a law of conservation of energy in a sense, right? So because the left hand side of the equation, that is 1 by 2 drs by dt square, it is basically the kinetic energy per unit mass. And then the gms by rs of t is basically the gravitational potential energy taken to the left hand side, it's minus. So basically it and then u is the constant of integration here. So we can say that the sum of the kinetic and the potential energy is basically constant. So in a way this also relates the is based actually on the law of conservation of energy. So what it also tells us is the total energy is basically constant for matter on the surface of the sphere as sphere expands or contracts under its own gravitational influence. So, and then since we consider the mass of the sphere to be constant as it expands or contracts, so we can express ms, that is the mass of the sphere, in terms of the density. So ms is equals to 4 by 3 pi r cube, that is volume, times the rs, which is 4 by 3 pi r cube, which is the volume times the density, that is rho of t. Even the density is also only a function of time. So since the expansion is isotropic about the center of sphere, so we can write the radius also to be only the scale factor times the radius of the sphere. So it is this is basically we're saying that the radius also is kind of a constant in this case. So where it is a scale factor and rs is the co-moving radius of it. We have seen the co-moving coordinates in the previous lecture. So if people who are watching this can also refer to my previous lecture to understand what is co-moving coordinates and co-moving radius. So we make these two substitutions for mass and radius in equation numbers. Equation number 4, and then we get the equation number 9, that is half rs square a dot square equals to 4 by 3 pi gr square rho t at square plus u. So we divide both sides of the equation again by rs square a square by 2, and then we get the equation number 10. So that is a dot by a whole square is equals to 8 pi g by 3 rho plus 2u by r square into 1 by a square. So this is basically the Friedman equation in the Newtonian form. But we already know that Newton's laws have limitations as such, and we have to go in the path of general relativity to understand the true nature of the universe. So basically we can modify the Newton's equation to get a equation that is based on general relativity. So let's see, so equation number 11 that is given in this is a dot by a whole square is equal to 8 pi g by 3 c square rho minus kc square by r naught square into 1 by a square is nothing but the modified Newtonian Friedman equation to a general relativity or Einsteinian Friedman equation. So I'm not going to go in depth with to derive basically from the Einstein's field equations, but we can understand the essence of it by just essence of this equation by just understanding the small changes that had to be done from the Newtonian Friedman equation. So the first change is the mass density, that is rho. In this case, as we can see here, rho has been replaced by okay, there is a small mistake. This has to be epsilon. Sorry, this is not rho, this is epsilon. So the first change that we did is we replaced the mass density by energy density and then divided by the square of speed of light. So we have from general theory of relativity, we know the concept of peculiar speeds, right? So if a particle of mass m is moving along in a space that is also is expanding or contracting, so the additional energy that the particle possesses can be given by this, that is square root of m square c power 4 plus p square c square. So if a particle is non-relativistic, then its peculiar velocity, that is v, is very much less than c. So then we can neglect the whole v term, and then its peculiar momentum will basically be approximately equal to mv, and its energy can be given by E non-relativist energy of a non-relativistic particle is approximately equal to mc square times 1 plus v square by c square, that is approximately mc square plus 1/2 mv square. This is for a non-relativistic particle moving in the expanding space. So but we know that the universe is not completely made out of non-relativistic particle. You also have light, which also contributes to the curvature of space-time, right? So you have the energy that is h nu or hf, for nu or f for frequency. So you have E is equals to h nu or E is equal to hf, which will contribute to the the energy, which will contribute to the curvature of the universe. So this is about the first change that we have to make. And then the second change that has to be made is to make the relativistic substitution. So we have the term here 2u by r square, we substitute it with minus kc square by r naught square. So the first general understanding is basically is that if u is greater than 0, that means the universe is negatively curved, because you have a negative sign and you have k to be negative right here. So if u is greater than 0, then the space is given to be as a negatively curved space. If u is less than 0, then it's a positively curved space, and if u is equal to 0, it is basically a flat space or a Euclidean space. So using this equation, we can also conclude, we can also get an idea about the curvature of the space that we are working with. And yeah, this is actually is very important equation, but Friedman equation as such, if it has to be more useful or to be more implemented in a typical universe, so we need to find a way of relating it with the observable properties. So we try to bring up the Friedman equation, and we try to find a relation with the Friedman equations along with the observable quantities like the Hubble's constant or the scale factor, etc. So from what we have seen in the previous lecture, we know the distance linear relation between the recessional velocity and the proper distance. So that is v is equals to h times the distance. So both, or in this, all the variables are only dependent on time and nothing else. So where h is equals h of t, that is the actually it has to be mentioned in the previous lecture. But the h of t is basically known as the Hubble's parameter, and h naught of t is basically the Hubble's constant at the present moment, at which the scale factor is equals to 1. So the Hubble's parameter h of t is equivalent to a dot by a. So when we try to make the substitution with the Friedman Einsteinian version of Friedman equation, or the actual Friedman equation, so we get equation number 16, that is ht square is equals to 8 pi g by 3c square. So you have, yeah, that correction was made here, sorry. In the previous part where I mentioned the Friedman equation, it had to be epsilon and not rho in the Einsteinian version or the general relativistic version. So it is 8 pi g by 3c square times epsilon t minus kc square by r naught square a square. So at the present moment, h naught is equals to h times t naught. So that is a dot by a. So we know the value of the Hubble's constant, right? So that is 70 plus or minus 7 kilometers per second per megaparsecond. So we can write the equation number 16 in terms of 18. So I mean 18 in terms of 16. So you can write h naught square is equals to 8 pi g by 3c square, again epsilon naught, as we are talking about the present moment. So you also make the substitution for the energy density here. So minus kc square by r naught square. So you might have seen that the scale factor term is missing, because at the present moment we try to normalize the scale factor and take scale factor to be exactly equal to 1 at the present moment. So with this equation, we can see that Friedman equation is, gives us a relation with H naught, which tells us the current rate of expansion, and then E epsilon naught, which tells us the current energy density, and K by R naught square, which tells us the current curvature of the universe at the present moment. So this since now that we've compared and we've formed a relation with the observable quantities, so from the we can make actual we can use the Friedman equation to find to understand the universe and how it behaves. So like how we've seen the general form of Friedman equation, the ht square is equals to 8 pi g by 3c square epsilon minus kc square by r naught times a. So for if we consider in the case for a flat space, we say okay, so then my k will be equal to 0 for a flat space. So my the second term in the right hand side will amount to 0, and then ht square is equals to 8 pi g by 3c square epsilon. So for a given value of Hubble parameter, there is a critical density. So the critical density is nothing but the minimum amount of density that the universe should possess. So the critical energy density, energy density, in density I mean energy density, that is equals to, so if we take all the terms to the right hand side and except for the the energy density, so you get 3c square by 8 pi g times ht square. So using the values of because all of these are constants on the right hand side, we can use the given values to find out the value of critical density at the present moment. Again, c comma 0, right? So if t naught is basically the present, it indicates the present moment. So you have 8.3 plus or minus 1.7 times 10 to the power minus 10 joule per meter cube. That is almost equals to 5,200 plus or minus 1,000 million electron volts per meter cube. And also the critical density, the critical matter density can also be computed by using this formula. This is based on the substitution we made earlier to convert the Newtonian form to the relativistic form. So you can compute the equivalent mass density. So this is 9.2 plus or minus 1.8 times 10 to the power minus 27 kilogram per meter cube. It's also equals to 1.4 plus or minus 0.3 into 10 to the power 11 solar mass per meter cube per mega per second cube. So if you want to make it into, if you want to understand the density in the real life, it is equivalent to like one proton or one hydrogen atom per 200 liters, or basically it is 140 solar mass equivalent star in in one meter cube mega per second. So this is way too way too low, but this is the critical density. As I said, this is the, but the values that we've got here is way too low. But there is a catch here. So our universe is mostly made up of intergalactic voids where there is absolutely very minimal density. So, but as I've said constantly over my last few lectures, that we are looking at scales that is above 100 megaparseconds. So at that scale, when we look at and we count in the intergalactic voids that are present in the universe, it gives us the correct result, or we get close to the calculated result we get here. So this is basically like a correct evaluation. So, and one thing is that when we try to talk about the energy density of the universe, since it is obviously increasing or it is varying with time, right? So when we talk about the energy density, we try to give it in terms of a ratio. Okay, so we name this ratio as the density parameter. So basically the ratio is basically the ratio of the energy density divided by the critical energy density. So this is so this value is basically like accepted through this relation is basically accepted throughout in like among the cosmologists, and they completely use this relation to compute the energy density of the, energy, give the relation in terms of energy density. So the value, excuse me. So the value of the energy density ranges from 0.1 to 2. So this is the the upper and lower limit of the energy density. The density parameter. So this is widely accepted to, for calculation purposes that we can use to compute the nature of the universe. So, and in terms of density parameter, which basically makes more sense in the real world, you know, real world conditions. So we tend to represent the Friedman equation in the density parameter, in terms of density parameters. So we can write it as 1 minus sigma, 1 minus omega of t is equals to kc square by r naught square at square ht square. So from with this we can, if we from this equation, if we since this right hand side is basically we can compute the value since it's all constants. So we can understand the curvature or the curvature of the universe as if the value of if the right hand side is complete, if the right hand side is less than 1, or if you say that the omega is less than 1, then for all conditions and for all time it will always be less than 1. Since since you cannot change this sign on the right hand side is completely positive. So if you get the value of omega to be always less than 1, so then it will always mean that the universe is completely contracting for all time, like throughout its existence. So it will never change the contraction throughout the course of time. So if the value of omega is greater than 1, then the universe will expand no matter what. Like it will keep expanding to infinity or whatever the end point is. And then if it is equal to if it is omega is equal to 1, then it's like constant forever. It's neither expanding or not contracting. So basically, like how you cannot ask the leopard to change its spots on its skin or on its fur, so you cannot ask the universe to stop expanding or stop contracting in the same way if the omega by getting the correct value of omega. So you cannot ask ask the universe to change its nature if its nature is determined by omega. So that is why the density parameter is basically very important and very essential to understand the nature of the universe. So now we move on to the next section, that is the fluid and acceleration equation. So the Friedman equation basically gives us a lot of info as such. It is very important and very crucial in the field of cosmology, but we don't get enough data about the time, the scale factor and the energy density. So we don't get much info about it, and we cannot directly compute the values of the scale factor and the energy density. So there is another equation which is which gives which opens the room for the Friedman equations, and through which we can get more precise observational values. So we know that the law, the Friedman equation was basically based on the law of conservation of energy, as we have seen before. And there is also another famous field or theory which also talks about the law of conservation energy, that is basically the thermodynamic equation, or the first law of thermodynamics. So we know the first law of thermodynamics is dq is equals to dE plus pdV. So q is nothing but the heat transfer, E is nothing but the internal energy of the system, and then P is the pressure, and then V is the volume of the system. So the cosmological principle states is that the universe is perfectly homogeneous and isotropic at all points. So we can say that there is no effective transfer of heat or net bulk flow of heat. So we can say that the change in heat in the universe at such larger scale, that is above 100 megaparseconds, so it will be equal to 0 for a co-moving volume, as you have the coordinates are basically co-moving coordinates that only change, depend on time or only move through time and not by itself. So as the universe expands, so the first law of thermodynamics, when applied to the expanding universe, reduces to E dot plus PV dot is equal to 0. So basically that's the derivative of internal energy and pressure times the derivative of volume. So as we have seen, as we have assumed, as we have using this relation before, since the radius is co-moving and the volume is basically co-moving along with the expansion of the universe. So we can substitute for the radius of these, the sphere or the surface to be equals to 8 times Rs. So if we make this substitution in the expression for the volume, so we have V is equals to 4 pi by 3 times R cube times 8A cube. So the rate of change of volume of the sphere is, if we have to differentiate the equation number 28, and then we get the final answer after differentiating, that is V dot is equals to V times 3 times A dot by A. And then the internal energy of the sphere is nothing but ET is equals to VT times the VT times the energy density. So internal energy is also a form of energy. So it depends the energy in a system. So we just express it in terms of the energy density. So that is volume times the energy density. So if we make these two substitutions in our equation, equation number 27, we get equation number 31, that is E dot is equals to V E dot plus V dot E, that is equals to V times E dot plus 3 A dot by A times epsilon. It's not E, it's epsilon. We also have for internal energy E. So if we combine equations 29, 30 and 31, we get the equation that is V times the epsilon dot plus 3 A dot by A times epsilon plus 3 A dot by A times P, that is equal to 0. So since we know the volume cannot be equal to 0, the term inside the bracket should be equal to 0. So the equation number 33 is called as the fluid equation, and it is also the second key to understand the expansion of the universe. So the Friedman equation and the fluid equation are both statements about energy conservation. As we saw, they both are based on the law of conservation of energy. So by combining these two equations or these two concepts, we can derive the acceleration equation, which actually tells us how the universe expands, how the speed of the expansion of the universe, becomes faster or slower with time, or how the universe expansion of the universe accelerates with time. So when we multiply the Friedman equation by A square, we get equation number 34. That is A dot square is equals to 8 pi G by 3 C square times epsilon naught A square minus KC square by R naught square. So if I want, I'll get my A dots to, A dots to one side, and we get the equation number 35. So that is, I differentiate equation number 34 to get equation number 35. So that is 2 times A double dot times A dot is equals to 8 pi G by 3 C square epsilon dot A square plus 2 epsilon A dot. So if we divide equation number 35 by 2 epsilon A dot, we get the we get equation number 36, that is A double dot by A is equals to 4 pi G by 3 C square into epsilon A by A dot plus 2 epsilon. So this is equation number 36. So if we use the fluid equation of equation of fluid and make this substitution, so we get epsilon dot A by A dot is equals to minus 3 times epsilon plus P. So this is and we take the epsilon and then we make this is the fluid equation. So this is given in equation number 33. So using the fluid equation, using this equation, we substitute it in the equation number 36, and then we get the acceleration equation, that is a double dot by a is equals to minus 4 pi g by 3c square into e plus 3p. So this is basically an equation which tells us how the universe accelerates as expansion, how the universe accelerates with time. So, excuse me. So we also know that the acceleration of the universe also depends on, includes the quantity, the parameter of pressure, which is also, which is based on the matter content that is filling the universe. So a gas that is there are, due to the presence of various gases in the universe, the gases are made up of baryonic. So baryonic matter, if you can also refer to the introduction to quantum mechanics lecture that is also posted in the same channel. So you can refer to that to understand the baryons and baryonic matter more precisely. So the baryonic matter, they are basically they are matter, the content, the atoms are made up, the particles are made up of 3 quarks. So I don't want to get too detailed into that. So you can refer to the other lecture to get more details about it. So the gases are made up of baryonic matter. They have a positive pressure. Thus, which results from the random thermal motions of the atoms or ions of the gas, which the gas is made up of. So a gas of photons also has positive pressure, as does a gas of neutrinos or WIMPs. So a WIMP is basically nothing but they are weak interactive massive particles. So they actually don't respond or they don't react to or like forces to forces or other things as such. They only react under special conditions, or like we only react to weak interactive forces, and they don't react to any other kind of forces. So neutrinos also come under the category of WIMPs. So the gas of photons also has a positive pressure, as is the gas of neutrinos or WIMPs. So the positive pressure associated with these components of the universe will also, because the pressure is positive, right? So what it will do is it will basically cause the expansion to slow down. So excuse me, sorry. So since this is causing the expansion to slow down, basically it means that but the rate of expansion should always be constant, as we have seen, or it should increase constantly. But since the presence of these baryonic matter in exert a positive pressure, so this causes the expansion to slow down. But so later we will also see that if the universe had a component, so this component is actually Easter egg for what I'm going to speak later. So if think that if the universe had a component which has a pressure less than minus epsilon by 3, so basically it means that it exerts a negative pressure. So that means that in order to neutralize that part, since to neutralize the effect of the positive pressure that is exerted by the baryonic matter. So the only thing we can think of is there is something in the universe that exerts more negative pressure in order to compensate for the positive pressure exerted by these particles. So this is an idea that people have thought about. So this later will be known as that the component is basically the cosmological constant, which we'll look in later as we go on with the lecture. So next thing is the equation of state. So since we also have an idea about the idea about the scale factor, and about the curvature, radius of the radius sphere, and then about the Hubble's constant, we have an equation relating all of these components. But now, since in the last category, the last section, we have introduced another new variable, that is the pressure. So we need an equation that relates the all the other quantities with pressure and energy density. So if we are able to successfully do so, we can easily compute all the necessary variables and all the necessary quantities to understand how the universe expands or contracts in the course of time, and we can understand the nature of the universe. So this would all be very easy to calculate the pressure if only pressure was directly or equal to the equal to all the pressure due to the matter content that is present in. But it is not so, and this is actually a very difficult job to compute the actual pressure of the universe in the case as we have seen in as the scientists or the people who work in the condensed state, the matter, the condensed states and stuff, they basically deal with pressure that is non-linear with the density of the particles that are present in the gas, or in a substance. So, but thankfully, it is not so for in the case of the universe, as we deal with low density gases of non-relativistic massive particles. And so, in this case, we can form a linear relation with pressure and the energy density of the particle, or of the half particles. So here the omega is nothing but your dimensionless number. So basically it's nothing but a way to a quantity that has been introduced to as a so that we can relate the pressure to the energy density uh, directly. So consider a low density gas of non-relativistic mass particles. So that is the kind of gases that we deal in cosmology or in the universe in large scales. So non-relativistic in this case means that random thermal motions of gas particles have peculiar velocities. So the peculiar velocities, as we have seen in the previous segment, which are tiny compared to the speed of light. That means the v, that is the velocity of the particle, is very, very, very small compared to the speed of c, that is the speed of light. So such a non-relativistic gas obeys the perfect gas law or the ideal gas law. That is, P is equals to rho by mu times kT. So when mu is nothing but the mean mass of the gas particles. So this is from thermodynamics, and the energy density epsilon of a non-relativistic gas is almost entirely contributed by the mass of the gas particle. So you have epsilon is equals to rho times c square. So if we want, in terms of epsilon, the ideal gas law can be represented as P, that is approximately equal to kT by mu c square times epsilon. So for a non-relativistic gas, again, the temperature and the root mean square velocity. So root mean square velocity basically is the square of the sum of the individual velocity times the mass divided by the sum of the velocity square. Excuse me. So this is all thermodynamics. Since you are including a lot of thermodynamics, these quantities are bound to show up. So you have a thermal velocity, that is root mean square of thermal velocity, that is the v square, and they can be related by 3 kT is equals to mu times the root mean square thermal velocity square. So the equation of state for a non-relativistic gas can be written of the form P non-relativity, the pressure for non-relativistic gas particles is equals to omega times energy density of non-relativistic gas particles. So where omega is nothing but your v square, root mean square of v square divided by 3c square. So this is basically like very, very less than 1, since v, as we considered, is very, very less than c, which is the speed of light. So most of the gases that we encounter in our life are non-relativistic. But gas of photons or other massless particles is guaranteed to be relativistic, right? So since photons are considered to have no rest mass, so they are the maximum speed that is attained. They have the maximum speed that is attainable by any particle in the universe, that is governed by the general theory of relativity. So although photons have no mass, they also have momentum, right? Since it doesn't have a rest mass, but since we see the moment, the photons are always traversing, so they have a momentum, and they exert hence they exert pressure. So the equation of state of photons or any other relativistic gas is P is equals to 1 by 3 times the energy density for a relativistic particle. Excuse me. And so the equation of state parameter omega, that is the equation of state parameters called, so can't take on any arbitrary values. So small perturbations in the substance with pressure P will travel at the speed of sound. So since if small perturbations, as in the small variations or small disturbances in the system, so the disturbance will carry out in the speed of disturbance in the form of pressure will carry out in the speed of with the speed of sound. So for adiabatic perturbations in a gas with pressure P and energy density epsilon, so the sound of speed relation is given by Cs square, that is the speed, the velocity of sound. Cs square is equals to C square times the dP by d epsilon. So if the substance, if any substance has the state equation of state parameter greater than C, that implies that the sound of speed Cs is equals to we know the relation sound of speed is equals to root of omega times c square. So that if omega is greater than 0, that means that the speed of sound is basically larger or greater than the speed of light, which is not the case, right? So this would violate the law of causality. So omega, see, the value of omega is restricted to omega less than or equal to 1. So these are the boundary conditions that we have to take in order to not violate the laws of causality. So why I have brought in the factor of equation of state parameter. So if the so in the case of the relativistic gas particles, we see that pressure is, since we saw the relation P is equals to omega times epsilon, and we see P relative is equals to 1 by 3 times epsilon of relativistic gas particle. So so the omega takes the value of 1 by 3. So omega is exactly equal to 1 by 3 only if the gas particles are made up of relativistic particles. And in the case of non-relativistic particles, where the velocity of particles is very, very less than the velocity of light, so in that case, the value of omega is less than 1 by 3. But there is also a case that we have seen and we have come to understand of a case wherein omega is less than minus 1 by 3. So we take this this condition to be very, very, very serious. This when if it is less than omega is less than minus 1 by 3, so that means it is exerting a negative pressure. So this basically is what people refer to as dark energy. So for the gas for a substance containing relativistic matter or non-relativistic or be it whatsoever. So if the gas is made up or anything is made up of particles that exert negative pressure such that the omega is less than minus 1 by 3, so though that substance called as dark energy. So we call it dark energy because we don't know much about it right as of now. So this condition implies the presence of as a quantity or a thing that exerts negative pressure. So this is referred to as dark energy, and basically this also gives a small intro to the cosmological constant that we will be talking about in the next section. So this is an interesting concept or topic to understand as one tends to pursue higher in the field of cosmology. You'll try to get to actual significance of the equation of state parameter, that is omega. So now let's get to the the most interesting part of this lecture, that is the cosmological constant that we have been talking about since the second segment. So cosmological constants is, the whole concept is basically contradictory, or it's kind of on and off in the field of physics as such, because the person who brought in the quantity, that is the cosmological constant, was the person who hated it the most, and that specific person called it the blunder of his, the biggest blunder of his. So obviously, for people who might be knowing, he is Albert Einstein. So Albert Einstein was the person who brought in the cosmological constant to fit in his the condition for a steady state universe. So that I have actually talked about in my previous lecture. So and then, like, when Einstein tried to fit in the cosmological constant only to make his goal or his assumptions to be right. So, but later it was found out that the cosmological constant was not just any factor that was put in to satisfy a condition of an equation, but it was also having a great or a very important a great of it was of great importance in the field of cosmology, that is realized recently, like 20-30 years back. So this is about the background of the cosmological constant, and now we can look at how you can come about it mathematically and how Einstein did it. So as we have seen from the Poisson's equation, Poisson's relation, that is the Laplace square phi is equals to 4 pi g times rho. So the gravitational acceleration A at any point in space is found out by taking the gradient of the gravitational potential. So that is acceleration is equals to negative Laplace of phi. So in a static universe, that is what Einstein had always wanted. Like, he just wanted the universe to not expand or not contract. He just wanted it to be as it is, and that is his condition that he wanted to show with this theory of relativity. So Einstein wanted to bring up an equation that would tell that the universe is static and it's not expanding or contracting as time progresses. So in a static universe, acceleration obviously must vanish everywhere in space, since there is no net acceleration, right? Since the universe, which Einstein wanted, was to be static. So the potential gradient, the gradient of the potential must be constant in space. So, however, if the gravitational potential is constant, then the relation, above relation becomes rho is equals to 1 by 4 pi g times Laplace square phi. That should be equal to 0. So, what Einstein did was, since this is not, this is not a good equation as such, because this is not true. So basically what it's telling is the mass density of the universe is 0. That means there are no particles to exist. And in that case, well, Einstein, you have got a steady state universe. But we know for a fact that the universe is made up of particles that have mass, and then they exert pressure and stuff. So what Einstein did was, to justify his equation, he just casually added a constant, that is this lambda, to his equation, to say that the equation, the universe can also be static. So you have Laplace square phi plus factor lambda that can justify which is mostly to negate the possibility of universe expanding or contracting. So it's equals to 4 pi g times rho. So here the lambda was called as the cosmological constant. So if we try to incorporate the lambda with Friedman equation, basically it is which is derived from the Einstein field equation. So our modified Friedman equation becomes A dot by 8 is equals to 8 pi g by 3c square times epsilon minus kc square by r naught square a square plus lambda by 3. This is the factor that is being added to to the Friedman equation to justify the addition of lambda in the Einstein field equations. And then, but one thing is to know that the fluid equation remains the same because it doesn't depend on that. So the acceleration equation does depend because matter is accelerating, and then you're adding a factor that does which negates the acceleration such that the net acceleration becomes zero. So you need to add the quantity to the acceleration equation. So that is a double dot by a is equals to 4 pi g by 3 c square times epsilon plus 3p plus lambda by 3 again. So in this case, in equation 51, so Einstein was able to justify, and it was acceptable that the lambda can take the value 4 pi, lambda can take the value 4 pi g times rho. So it was acceptable by using acceptable by the laws of physics that lambda can take that value. But so Einstein had he just put in a constant or quantity in order to justify his steady state universe. And but what Einstein, he was not happy with what he had done. It was not profound, or it was not like it didn't have any specific significance, and it was just there to just satisfy his equation, right? So Einstein was not happy, and he wanted to understand about the nature of the cosmological constant. And so we have the Friedman equation, and then even your energy density is based on the density of the particle. So I mean density of the universe. So you have energy density is also equivalent to c square by 8 pi g times lambda. From this equation, if you substitute a dot double dot to be 0, you get the equation. And so the fluid equation also tells us that to have the lambda constant with time, you also need to have a pressure a pressure factor that is also to be taken in consideration, because density also is to be constant. So you have pressure in terms of the lambda is equals to minus energy density times lambda, that is minus c square by 8 pi g times lambda. So if the double derivative of acceleration is 0, that means that the universe with matter density rho and cosmological constant lambda, the acceleration equation also reduces to that is equation number 53 for reference. You can view here. So if we substitute for a double dot, which I talked about, is to be 0, so you have minus 4 pi g by 3 times rho plus lambda by 3. So if a dot, that is also, it has to be 0 since there is no net acceleration, is equal to 0. The Friedman equation reduces to 0 is equal to 8 pi g by 3 times rho minus kc square by r naught square. Again, we didn't take the scale factor here because it is at the present moment, as you can see with the r naught plus lambda by 3, that is equals to 4 pi g 0 minus kc square by r naught square. So and what was actually the implication that Einstein had made by introducing this, constant? So he termed it as the gravely. He termed the cosmological constant as it was a gravely detrimental, constant to for the formal beauty of the theory. As I said, because it doesn't make any sense to randomly add a constant and then be okay with it without understanding its actual significance, and to just make your theory possible or make sense. So although Einstein's static model was in equilibrium, since in order to negate the acceleration of the universe due to the pressure of the particle, presence of pressure in the particles of the universe, so the cosmological constant should also exert enough pressure to negate to nullify the increasing pressure of the universe. So but what was observed that as time progressed, right? So since we also want the pressure due to the the acceleration due to of the cosmological constant to be always constant. For the name says it so. So but then what you have is, yeah, the energy density, or the energy of the energy density will all like will decrease with time, right? As we have seen, as the universe is expanding. But Einstein wanted the lambda to negate that as. But as the excuse me. So yeah, the energy density of the lambda remains unchanged, but the energy density of the matter drops. So then, thus the repulsive force is greater than the attractive force is what we can see here, right? Because and, as we see, as time progresses, the energy density of the matter content in the universe will decrease, but the energy density of the cosmological constant remain constant throughout time. So as it keeps decreasing, as with relate in with, with relate in relative to the matter density, the energy density of the universe, that means the cosmological the energy density of the cosmological constant is increasing with time in relative to the energy density. So what it means is the repulsive force is increasing as second by second as time progresses. So if the repulsive force is increasing, again you have your energy density to decrease even further. If the energy density decrease even further, the repulsive force again increases. So it's an it's an on and ongoing process that results in the universe to expand no matter what. So as Einstein was even Einstein was even more surprised with the result by just introducing a small constant just to satisfy his steady state equation. So after Hubble had discovered, after the Hubble's law was, paper on Hubble's redshift, Hubble's law and Hubble's redshift was, published. Einstein was so eager and so willing to like disregard the whole concept of cosmological constant. But it was as scientists, began to accept the blunder of Einstein's field equation. They began to accept and accept us completely, and they tried to find out the true what the cosmological constant actually means. So um, so the next thing what we go here is, yeah, okay, so what it actually so excuse me, I'll just drink some water. Okay. The question that since Einstein has brought in this constant, so the question that was already always asked was, what is the physical significance? As I said, the people after Einstein, they tried to accept the constant, and they tried to find out more about what it actually means and what is its significance in the universe. So in order to give the cosmological constant a real physical significance, we need to identify some component in the universe whose energy density remains constant as the universe expands or contracts in any case. So that is one possibility, that it has to be a vacuum space. So, but currently, so the research or the theory of vacuum energy is being, done even now in the field of quantum field theory. So, in classical physics, obviously, we cannot make any sense, since vacuum is, termed to have like no particles as such. But if you consider in quantum mechanics, it allows, the existence of particles even in vacuum. So even Heisenberg's uncertainty principle tells us about the particles that are generated, particles and antiparticles generated always in pairs, and then they annihilate each other, and then they just get released as energy, and they go back to being the particles cease to exist. So using the Heisenberg's uncertainty principle, you can have the del E times del T is less than or equal to h. Sorry, the T here is basically the time, not just to be clear. So this was a sort of an intriguing concept. So just as the energy density is associated with the real particles in the universe, so we also have energy density that corresponds to the particles in the vacuum. That are the particles that exist in vacuum. They like form in particles and antiparticles, and they try to annihilate each other. So particles are called as virtual particles because you cannot always expect them to exist. They just exist for a certain brief amount of time, that is matter of less than a second. So they exist and then they annihilate each other, being energy. So these are called as virtual particles. So the vacuum density, that is epsilon vacuum, is a quantum phenomena. So, and it is a quantum phenomena, and it doesn't actually it doesn't care whether the universe expands or not. It just is constant forever right there in the vacuum space. So so as we have seen that you also have an energy density for the vacuum. So people in the field of even now, people have not been able to get a precise measurement or a precise value for the energy density of a vacuum. One suggestion that was that was given was the natural vacuum density is nothing but the Planck energy density. So so in this equation 60, we can see the energy density of vacuum is approximately equal to the EP by L cube of P. So this is the Planck energy and the Planck length. So since we know from in my first lecture, yeah, I mean in my we have covered the Planck length, Planck energy and stuff. So you have a Planck energy to be a constant, which is equals to the 1.2 into 10 to the power 28 electron volts. This is for a large body in particle physics. So this is for a large body, and then you have the Planck length, that is nothing but 1.6 into 10 to the power minus 35 meters. Extremely small. So if we use these constants and plug into the equation number 60, you have the value that is 3 into 10 to the power 133 electron volts per meter. So that is absurdly great for universe. So this is not correct and not accepted by scientists and the scientific community throughout. But this is one way that we can think about one thing, like how the what actually the cosmological constant can actually mean and what it can signify in as to the expansion of the universe as we see it today. So with this, I will end my lecture here, and thank you for your patience, and we can open the room for questions. Good.